So let me start by just recapping what we were doing in the last lecture. So we're looking at the Reiste-Nordstrom de Sitter black hole as an example of a black hole with a Cauchy horizon whose stability we're understanding. So I've drawn the Penrose diagram, or the relevant part of the Penrose diagram again here. So this is the region exterior to the black hole. So this is the black hole event horizon. We're in de Sitter, so we have a cosmological horizon here. And up here is the black hole interior, which has a Cauchy horizon. And we're going to be focusing on this right-hand component of the Cauchy horizon because that's the most physical one, the one most relevant for a real black hole formed in collapse. So last time I explained that we're setting up the problem of perturbing this black hole as a characteristic initial value problem, which means we're specifying initial data on these null hypersurfaces, so this one and this one. So we've got a bunch of wave packets which we're specifying on those surfaces, and so we want to evolve the resulting solution and figure out what happens up here. So last time I was mainly talking about what happens in this region, that's region 2, and so I started from a characteristic initial value problem in region 2 where I introduce an auxiliary wave packet Z tilde on here and explained how you figure out what the solution is doing up here in region 2 in terms of Z and Z tilde. So we saw that we could split the solution phi into two parts, an outgoing part and an ingoing part. So outgoing means it's doing this, ingoing means it's doing this. The outgoing part is smooth at this point of the Cauchy horizon, and the ingoing part in general is not smooth. And so that's the interesting part for us. This is the part that's going to enforce strong cosmic censorship if it's going to be enforced. So in terms of the Eddington-Finkelstein coordinate little v, the Cauchy horizon is at v going to infinity, and as v goes to infinity, this ingoing part just takes this simple form here in terms of this data Z and Z tilde, and these scattering coefficients that I defined last time, which relate the basis of mode functions down here to the basis of mode functions up here. So to evaluate this quantity, since we're interested in the large V behavior, it's straightforward to do that by deforming the contour for the omega integration into the lower half plane like this. So we bring the contour down to here, and when we do that we're going to pick up contributions from any poles in between these two contours, and it turns out these poles are going to dominate the contribution from this new contour of integration. So the dominant contribution near the Cauchy horizon is just determined by these poles, as I've shown here. Yeah.
If you make the perturbation in the region 1 only, then how does the Z get a support? I mean, how does Z arise?
Well, Z is supposed to capture whatever is happening down here, or maybe it captures something about the details of the gravitational collapse. I mean, it's just more data we can put in. I mean, ultimately, it doesn't actually do anything.
Okay, so only from the region 1 I would be able to perturb it so that the singularity is created?
Yeah, you could set Z to 0, in fact.
Okay.
Yeah, for completeness, we've included it. It doesn't really do anything very interesting. Yeah, so if we look at this contribution here, so now we got a contribution from the pole terms. This is little v here. So to look at how smooth this is at the Cauchy horizon, we want to write it in terms of coordinates which are regular at the Cauchy horizon. So these were the Kruskal coordinates I defined last time, which look like this. So we've got u minus and v minus. And region 2 is down here, and then this is the Cauchy horizon, which is at v minus equal to 0. And so when we convert this into an expression in terms of v minus, it gives us this power of v minus. And because this is not going to be an integer, in general, this is not going to be smooth. Okay, so the question is, how non-smooth is it? Is it differentiable? How differentiable is it? And now you can see, see that's all determined by these poles.
Sorry, the poles, were they both in B and E tilde?
No, so these are just any poles in this entire expression.
Okay.
So I've already told you that there are poles in B and A tilde, but these are unphysical. Okay, so I told you the poles in one of them, I've forgotten which. The poles in one of them gives you integer powers here. And the poles in the other one gives you non-integer powers, so in principle they're non-smooth. But as I'm going to explain now, actually, the coefficient of those poles, which I've not written here, turns out to be 0. And so they just drop out, they're unphysical.
But the other one was presumably A tilde.
Well, let me remind myself.
The one which could have been dangerous. It's from the ingoing.
A tilde was the one that could have been bad, yeah, that's right.
Oh, good.
Yeah.
So the fact that the poles were manifestly not a problem for B was the statement that Z is not doing anything interesting, right?
No, it wasn't. Well, it wasn't so much that statement. It was the reason that they weren't physical is that when you evaluate this expression, this turns out to be an integer, and so you get V minus to a positive integer power, and that's smooth. So.
Right. Which isn't that the statement that the Z could not have been causing trouble?
Okay, well, yeah, I guess that's, yeah, okay, I guess you could phrase it like that, yeah. So for any choice of Z, that's not going to do anything interesting, yeah. Yeah, in principle, it could be poles in Z. I'm not going to discuss that, but they have been discussed in our paper. And you can see that they don't do anything. Although that is actually quite a confusing point. Okay, so let's now look at this other region, 1, and try and solve the scattering problem in region 1. So, region 1. So now we've got initial data x and x tilde, and it's going to scatter to produce some outgoing wave packets. We want to calculate z tilde in terms of x and x tilde to understand the analytic properties of z tilde. So to do that, we need to introduce some mode functions in region 1, which I mentioned briefly at the end of the last lecture, but let me just say that again now. So in region 1, we're going to define R in plus and R out plus. These are defined by their behavior at the event horizon, which is R star goes to minus infinity. So as before, so it's exactly the same definition as we did in region 2. But now we also have to discuss the behavior at the cosmological horizon. So we define a new pair of modes, R in C, C for cosmological, and R out C as e to the minus I omega R star, or e to the plus I omega R star, as R star goes to infinity. Okay, so R in C are modes which are going to be smooth at the past cosmological horizon. R out C will be smooth at the future cosmological horizon when you multiply by e to the minus I omega t. Okay.
R in and R out, are they the initial states for region 1 or the final states for initial 1?
So remember last time I wrote down a radial equation, which is an ODE, and we want the modes to be solutions of that ODE, and I'm defining solutions by their asymptotic behavior as R star goes to infinity. Yeah, so this defines a pair of solutions of the radial ODE. Okay, so then as we did before, to work out how we take data down here and get data up on the event horizon, we need to solve the scattering problem. So we need to write this C basis, defined by its behavior at the cosmological horizon, in terms of the plus basis, which is defined by its behavior at the event horizon. Okay, so to change the basis, let me write it. I'll write the plus modes in terms of the C modes in this expression. So I'm going to write the coefficient like this.
Sorry, and now in region 1, last time I was confused about space and time, but in region 1, these are really like e to the pi kx's, right?
Yeah, this is
really like a Mersbacher scattering problem.
Yeah. This is a standard scattering problem now. Yeah.
Which one was smooth on
H minus would be R out plus.
So you want R out plus would be smooth on H minus could cause potentially can cause trouble.
Yeah, so the point is that if I take, let's see, R out plus, these are smooth down here, but they're badly behaved on the event horizon,
Therefore, that can
future
cause
event
trouble
horizon.
to get.
No, because we're going to look at superpositions of these things. When we superpose these, we can build wave packets which actually vanish up here. Okay, so by superposing R out plus, you can build. So R out plus is a set of modes which forms a basis for wave packets which look like this. Okay, so there's an outcoming wave packet here and it's 0 up here. Okay.
So it will be the one that is regular on C minus then? Which one is going to give me the late time behavior of Gentile? This is the question I'm asking.
Well, we're not going to look at individual modes. I mean, we're going to have to look at sums of modes because we've got incoming data from here and here. Okay, and we're going to need to relate it to things. I guess what you're asking me is what looks like this. Okay, so then we just have the ingoing part here and no part here. Is that what you're asking?
Yeah, the part that will contribute.
Yeah, so this is the, these are the in-C modes. Okay, so I've got incoming wave packet here and nothing here. Okay, yeah, it is quite confusing, this whole thing, but I couldn't find a clearer way of explaining it. Okay, so what I've done here is I've just written the plus mode here in terms of the C basis. Okay, and so I've introduced some coefficients R and T, which I've called R and T because they are transmission and reflection coefficients. So T and R are the transmission and reflection coefficients.
So, sorry, plus means at early times they're supported?
No, plus means they're defined by reference to the event horizon, and C means they're defined by reference to the cosmological horizon.
Right. So I'm thinking of this as a scattering process.
Yeah.
So for me, what you've called C minus and X are early times, and what you've called H plus and C plus are late times.
Yeah, but it's a bit confusing. The modes themselves are not defined by early and late times. They're defined by R star goes to plus infinity or R star goes to minus infinity.
Okay.
Okay.
But for the physical process of scattering, this is the data you specify, and that's what you get out, right?
Well, this equation basically tells us about scattering. Okay, so we're sending in R in C. We're sending something in from down here, from down here, and it's scattering to produce something which is going in across the event horizon. So we're sending something in from down here. So if we superposed, if we took a superposition of modes to build a wave packet that was coming in from down here, there'd be nothing here. And then, so what I'm writing, yeah, let me rearrange this equation. I could rearrange it to write R in C in terms of R in plus and R out C. Okay,
if you could just label all your diagrams. So that R out plus is made out of superpositions of what, please?
R out.
Each of the diagrams, if you read.
This one is made, well, out plus here, this is just showing you what if you took a superposition of the out plus modes, you could build this.
Good. So that's made out of R out plus?
Yeah.
And R in C is, okay, it's made out of R in C.
Yeah,
I see.
yeah.
Yeah.
So what this equation is doing...
And there are two other diagrams like this?
Yeah, so there are 4 diagrams in total.
Could you draw them?
Each one has an empty space on the box.
Yes.
So if I do, let me do in plus. Sorry, I've done this wrong. Out plus is not this. Out plus is, no, that is right. Out refers to outgoing. This is an outgoing wave packet. Yeah, that's fine.
That's outgoing. And
Yeah, this
plus
is in plus would be this.
At late times.
In plus is this. So it's ingoing at the event horizon. So it's an ingoing wave packet.
Ingoing. And ingoing, but you're specifying your boundary conditions at what I think of as early times.
For this mode, you're specifying the boundary conditions here.
Well, what you're really specifying is that
No,
that
but
is zero,
but
right?
that's the superposition which is making that zero.
Right, that's what I mean.
The actual modes are defined by their behavior up here. We're saying that they behave as e to the minus I omega r star as r star goes to minus infinity.
That's fine. But what's special about these modes is that their superpositions give you zero on that.
That's right, yeah. So those modes are smooth here, but the individual modes are singular here, but by superposing them, we can build wave packets which look like this.
Okay.
Yeah.
Okay. And the last one?
Oh, the last one will be out C. So out is in this direction, so that will be this. So it'll be 0 here. Okay?
Okay.
Right. Sorry?
The picture of sending in something and causing some z tilde would be this in plus diagram, right? In C.
Sending in something from where? So that here in C, you're sending. So in C so this shows something rather special. It's defined by. So in this, you've got vanishing at late time here. So this is more like start with a wave packet of the future horizon and nothing on the future cosmological horizon. Evolve it backwards and see what you get. That would be a way of describing this. So the ones that are relevant for scattering are going to be this one and this one, which are the ones appearing in this equation. Okay.
One more request.
Yeah.
If you could put the whole Penrose diagram somewhere.
The whole Penrose, yeah, it's up here.
So
Oh, you mean with all
with
four?
everything, so you can see physically what was what.
Okay. Let's put it up here. I'm afraid.
And then that goes that way.
So this is 1, this is 2.
The corner between 1 and 2 then becomes a horizontal line.
So what becomes
That goes where 1 meets 2, there's a horizontal line.
where 1 meets 2? What do you mean a horizontal line?
This edge then has a horizontal line like this.
Here? Oh, you mean here?
Yes.
Oh, sorry. This is no infinity. Sorry. Yeah, space like infinity. So,
Yes.
that's right. Yeah. Yeah. Okay. So we're not really worrying too much about what goes on beyond the cosmological horizon.
But
But
I
yeah.
just want to understand what physically each of the piece of data was.
Yeah.
So so now the diagram that you had with data only here was stuff that came from early times in ADS, whereas the diagram with data only here was stuff that came from the white hole.
Yeah.
Okay. So that's why I think Abhijit, I would also have said what Abhijit said.
Yeah. So this is coming out of the white hole. This is coming out of the white hole. This is coming in from early times into situ. Yeah. But the way I'm thinking about this is this is just a means of setting up a general class of data in here.
Right.
I don't necessarily think there was a white hole or the. It's just more mathematically. It's much easier to set up data on null surfaces here than it is on a space-like surface, which is what you might normally think of doing.
Which one is the data that is really coming from the infinity, not from the white hole?
So this here is x tilde is coming from this region down here, which would be from past infinity. Yeah.
People who live in ADS have said that.
DS. We're not we're not in ADS. Not yet, but we will be soon.
And that is in these 4 diagrams, which one? In these 4 diagrams. And E plus is regular high? It is regular at some point, right? Why is it regular?
So in plus are the modes which are defined to be smooth here. On the individual modes of definite frequency are smooth up here. Yeah.
Isn't in plus defined by saying that it's 0 on the white hole horizon?
No, it's defined. So remember, so that the individual modes of definite frequency are defined by this kind of equation.
Yeah.
Okay, and it's only by taking superpositions that I can make them vanish on the white hole horizon. The actual individual singular there.
See, one way of thinking of it is the in plus are the ingoing modes in ancient frequency.
Yeah.
So they're smooth here.
Yeah.
Now you take superpositions of these, they're basically modes going like this. So they never came out of here.
Yeah.
The ones that were smooth here are the ones that were Z, when you make wave packets are Z.
Yeah. Good. Okay. So now we're doing this change of basis, and this is basically defining some scattering, so some transmission and reflection coefficients. T and R. So these are basically transmission and inflection coefficients for waves coming out of the past cosmological horizon. So this kind of wave. Okay, so in other words, we're taking modes with definite behavior at the past cosmological horizon, these in-C modes. Okay, these are ones coming in from the past cosmological horizon, and we can write them in terms of modes going into the future event horizon and modes going out of the future cosmological horizon. So this describes scatter. So if we multiply this whole equation by T, then the left-hand side is the part that's transmitted into the event horizon, and this bit here is the part that's reflected back out to the future cosmological horizon. Okay, so it's basically this. Okay, so we've got stuff coming in from here. Part of it is transmitted, and part of it is reflected. Okay. And we also need to decompose the other set. So we can write R out, C, in terms of another set of transmission and reflection coefficients, this time with tildes. So this describes scattering of waves coming out of the past event horizon into waves that are transmitted through the future cosmological horizon. So we get stuff coming out of here. Part of it is transmitted through here, so that gives us T tilde, and part of it is reflected into the black hole. That gives us R tilde. Okay. So we've got two sets of transmission and reflection coefficients.
Two sets of initial data.
Yeah, exactly. By just rearranging the formulae, you can show that Z tilde, remember Z tilde is what's coming in here, and X tilde in the way you'd expect. So Z tilde is X tilde times T. So in other words, the direct transmission of this part plus X times R tilde. So the reflection of this packet into the black hole. Okay. So exactly what you'd expect. Good. So I need to refer back to...
Do we need X to be non-zero to see the behavior at all? To see the fact that we will have some late time tail in Z tilde?
No.
Can we make X to 0?
We could do, yeah. Right. Let's go over here. So we can learn quite a lot by writing down formulae for the transmission and reflection coefficients using the Wronskian. Okay, so if we define the Wronskian of two functions of R or of R star, just in the usual way, then it's straightforward to take this definition of the scattering coefficients and get a formula for them in terms of the Wronskian. So that equation tells us that T is given by the ratio of the Wronskian of R in C with R out C to the Wronskian of R in plus with R out C. Okay, so I think what horizon, and that becomes just the frequency. Okay. Same thing for the other coefficient, R tilde becomes the following. So now, just from this, we can learn everything we need to know. So first thing is, why did we get this cancellation? Why were these poles that we saw before unphysical? Why did z tilde have a 0 at integer multiples of minus I kappa plus? And the reason is, I told you last time that the mode functions in plus actually have poles. They have poles at negative integer multiples of I kappa plus. Okay? Which means that since in plus only appears in the denominator here, this whole expression here has a 0 at that location, as does this. Okay, so both t and r tilde have zeros. At poles of r in plus, which obviously the negative integer multiples of I times kappa plus. And so if these things, r tilde and t, vanish there, then there's z tilde from this expression. Okay, so that tells us that z tilde of minus I n kappa plus is 0, as I claimed last time. Okay, so that shows that the poles were unphysical. So what is physical, on the other hand, is the fact that E and R tilde can have poles, and they have poles when this Wronskian, which is the same in both, in the denominator, vanishes. Okay, so we get T and R tilde have poles where this Wronskian of R in plus with R out C is 0. Okay, so what does that mean for the Wronskian of these things to vanish? Well, it means that one of these things is a multiple of the other thing. Okay, so that would mean that R in plus is proportional to R out C.
So, Harvey, this is probably a stupid question, but last time you were analyzing the wave equation inside region 2.
Yeah.
You were making statements about poles and so on of that. And now you're talking about inside region 1. They're somehow the same thing?
Well, no, the point was I reduced the whole problem in region 2 to understanding the analyticity of a certain quantity. Where is it? That thing up there. Okay, and that quantity involves z tilde. And so the reason I've now gone to region 1 is I'm trying to understand what the properties of z tilde are.
Right. No, I understand the logic. I was just wondering why the algebraic properties of these Rn pluses. Last time you got poles because some Rn pluses, some functions had poles in region 2. Mm-hmm. You're now saying that they're cancelled because...
Well, the poles are poles in omega, right? They're not poles in a certain region of space. The poles in the...
So, but the wave function was being studied in region 2?
Yes.
The wave function now is being studied in region 1?
Yes.
Why isn't it a different problem?
Yeah, well, you're right. In principle, I mean, so this is now in region 1. So I said that the modes are in plus in region 1. I've defined in the same way as in region 2. But in principle, they are different modes because, in particular, the out plus modes are not smooth across the event horizon. They don't smoothly connect. But nevertheless, what I told you about the analyticity properties of these modes last time is exactly the same. It's determined entirely by the behavior at the event horizon. Yeah.
Thank you.
Yeah.
So I have a question. I was wondering if one way to think about this might have been that I know it's convenient to do compute these coefficients by breaking it up into region 1 and 2, but in principle you could have set up a problem where you specified initial data on the cosmological horizon and then directly tried to propagate that into the inner horizon. And I guess the point is that in that setting you don't expect any poles at the at 4 omega being at the outer horizon frequencies because that somehow just doesn't matter.
Well, I mean,
would that be one intuitive way?
I mean, I'm not sure what you mean because that is effectively what we're doing. We are setting up data on the cosmological horizon. So where's my picture gone? So one of our
I was just trying to.
One of our wave packets is on the cosmological horizon.
Yeah, I was just trying to intuitively understand the absence of poles at omega being multiples of k plus in the final analysis. And so I was saying if you thought of the entire problem, then it would be natural not to expect perhaps poles at
Oh, I see
omega
what,
being multiples
yeah,
of k plus.
yeah, I see what you mean. Yeah, so if you view it as just, a characteristic initial value problem where you have one branch, which is the cosmological horizon, and just view the other branch as just one branch on its own, then that sounds plausible. That's a good way of understanding why they have to cancel out. Yeah,
So because it's not a special surface in any way.
yeah,
Right? Yeah, that sounds great.
Yeah.
That's it. But on the other hand, I'm a little worried about this argument I just gave because it sounds too general. It sounds like it would work in almost any setting. It sounds like it would work in ADS,
It does.
that the outer horizon should never be special. So there should be something wrong about this argument that I just gave.
I don't think there's anything wrong with the argument. I mean, another way of thinking about it, it would be rather surprising if something so simple as the surface gravity turned out to play an important role in wave propagation. So for example, as we're going to see, let me just say a few more words, and then maybe I'll make that remark. So I'll say a few more words related to this equation I've just written down. Why are there poles? Okay, so this is why I haven't told you this in detail, but when you solve the equation to determine these mode functions, the method of solving... well, no, the boundary condition is that it goes like e to the minus I omega r star as r star goes to minus infinity. You solve it by converting to an integral equation, which you then iterate using a green function. And as was pointed out last time, when you do that iteration, you see these poles emerging, basically. So when you look at those expressions. In ADS, on the other hand, when we look at BTZ, you can see this completely explicitly. These are just hypergeometric functions, and you get poles. You get poles there. Okay, so what are these poles in the transmission and reflection coefficients? Well, they're when this Wronskian vanishes, but vanishing Wronskian means that R in plus and R out C are linearly dependent, which means that these are modes which are both smooth, which are smooth at both horizons. So definite frequency, which is smooth at the future event horizon and the future cosmological horizon. Okay, that's precisely the definition of a quasi-normal mode. Okay, so the poles in T and R are precisely at the quasi-normal frequencies. Okay. So the comment I was going to make just now is quasi-normal frequencies in general are not given by simple expressions for a general black hole. They're not simply related to surface gravities or anything like that. In practice, they have to be determined numerically. Yeah. So this would be my going down again. The modes are modes in region 1, smooth along here and along here. Modes of definite frequency. Yeah.
So HR is just, of course, the future event horizon.
Yeah.
And that C plus plays the role of infinity in flat space, for
Yes.
instance.
Yes. Yeah.
Or the boundary of ADS.
Yeah. So they're outgoing in both directions, if you want. Yeah. Okay. So Well, these modes were defined to be smooth at the future event horizon, and these are defined to be smooth at the future cosmological horizon. So if they're proportional, they'll be smooth at both. Okay. Yeah. Sorry?
More than just that they're smooth.
No, that's pretty much it. They have definite behavior, so that they go like e to they have definite frequency, so they go as e to the I plus or minus I omega r star. Okay, so all of this argument was essentially down by in 90, although perhaps not quite in a totally clear way. But the conclusion is then the distance that we could displace our contour into the lower half plane is determined by the quasi-normal mode with the smallest imaginary part. So it's determined by the frequency, let's call it omega star, of the low quasi-normal mode. By lowest, I mean the slowest decaying, or the smallest imaginary part.
Now there is a fight between the poles in Z and the poles you had in A and B.
Now, remember the poles in A and B are, I said, were all unphysical, they all cancel out. So either they give you smooth behavior, or they get multiplied by 0. Okay, so the only...
So it's the poles of Z that matters now?
Sorry? It's only these poles now that matter. These are the only poles that are left. Yeah, these are the only poles. So it's useful to define something called the spectral gap. Alpha is minus of this thing. Okay, so here's the omega plane, here's our pole omega star, and that's alpha. Okay, so it's the distance of the lowest quasi-normal mode from the real axis. Okay. So essentially this gives you the
So
rate of decay of generic perturbations in region 1. Yeah, question?
I have a question. Just to understand clearly, do I understand correctly that you're saying that the Chandrasekhar and Hartle analysis, which basically relied on these surface gravities, is maybe technically correct, but actually misguided because it misses this fact that you should really do the perturbations from outside?
So I missed the first part of your question.
So the question is the Chandrasekhar and Hartle analysis, which
Yes.
I think relies effectively on these surface gravities.
Okay, Chandrasekhar and Hartle were interested primarily in asymptotically flat black holes. And there it's different because you have a branch point at omega equal to 0. And it's that which dominates the behavior. Okay, here we don't have any branch points.
I see.
We just have a singularity. A pole, sorry.
I see.
Yeah, so that's the difference.
I see.
And that branch point is coming from the fact that in asymptotically flat space, you have power law decay rather than exponential decay.
I see.
Whether Chandrasekhar and Hartle did the analysis both in region 1 and 2, or just in 2?
They did it just in 2, but they put in the decay that you would expect along the event horizon from...
Behavior of Z tilde, they knew what it was.
Yeah, they knew there would be power law decay in region 1, and so they put in appropropriate behavior for Z tilde. Yeah,
The important part.
They knew the result.
Yeah.
Well, in fact, they discussed a range of possibilities for the possible behavior of Z tilde and said what would happen in each case. But I think they knew what they were doing, I think, for the actual behavior. Okay, so we can now write down the final answer. So the non-smooth part at the Cauchy horizon is proportional to V minus power minus I omega star over kappa minus at the Cauchy horizon. And if we split it into its real and imaginary parts, this is, I'll call that beta minus I times the real part over kappa minus, where I'm going to define beta to be the ratio of alpha to kappa minus. Okay. So it's this real part here which is the interesting bit. This is just giving some oscillations, the imaginary part. As I mentioned a couple of times, there was quite a lot of controversy over the 90s about whether this analysis was actually correct and whether it leads to the right answer. But in 2015, a couple of mathematicians, Hintz and Vashi, did a more mathematical or rigorous analysis and came to exactly the same conclusion. Okay, that this is the smoothness at the Cauchy horizon is determined by the value of this parameter beta, the ratio of the spectral gap to kappa minus.
Sorry, kappa minus is kappa where?
Kappa minus is the surface gravity of the Cauchy horizon. Okay. Good. So we can conclude that.
Is there no simple formula for
No. Yeah, it has to be determined numerically. So the conclusion is that phi in is ck at the Cauchy horizon if beta is bigger than k, and only if. So if you want the field to be C1 there, for example, beta will be bigger than 1, or if we're interested in strong cosmic censorship, then we might not want the field to be C1 at the Cauchy horizon, which would mean that we want beta to be less than 1. Okay, so the question of whether or not strong cosmic censorship is true is basically now a question about what is the value of beta. So putting that forward, so if beta is less than 1, then phi in is not C1, which would give out the Cauchy horizon. And then by back reaction, you would expect that to cause a curvature singularity to form. Okay.
Is not an integer?
It's
Not an integer.
no, it's just something that has to be calculated.
Will depend on the radius of the black hole.
It depends on the black hole parameters. That's all it depends on, is the black hole parameters.
Supposed to be an integer, what?
When it happens to be an integer, I'm not sure it ever does happen to be an integer. So yeah, the spectral gap alpha is not some simple thing. It's not, well, the exception is BTZ when I'll tell you what it is, but in general it's a complicated thing that has to be determined numerically.
And so it depends on the black hole parameters and also the radius of de Sitter space.
Yeah.
But you have these many parameters to play with, so can you not prune them so that this becomes an integer?
Well, the point of strong cosmic censorship is that we want this to be true for all black holes. If we can find any black hole for which this is bigger than 1, then we've lost predictability for that black hole. And so we'd say that physics isn't predictable in general. Okay? So this has to be less than 1 for any black hole. On Tuesday, I discussed the fact that even if you have a curvature singularity, it may still be possible to go through it. Yeah.
If you are in ADS,
Mm-hmm.
then would you have some statement like this?
Yes. Yeah. This all goes through in ADS as well.
So in ADS, then what is the value of beta when there is a superradiant instability in the verge of superradiant instability?
Okay. So I guess, yeah, I haven't thought about. I mean, if you had actually an unstable black hole, I don't think we would be interested in its Cauchy horizon.
Right. This is why I'm asking that. What is the value as long as I can trust this solution?
But wouldn't it be 0?
What be 0?
If you are at the verge of superradiant instability, the lowest quasi-normal mode has 0 real part.
Yeah.
So wouldn't that just be beta equals 0?
Yeah, but if you actually had an instability, you'd have.
No, but suppose we approach.
Okay, you're just on the threshold.
Yeah,
Yeah, I guess it would be going to 0.
Because it's determined by the real part of the quasi-normal.
Yeah.
Yes, and then you the solution is still reliable because you haven't crossed it, because you haven't crossed the bound. So the solution is still reliable, but beta is small enough so that is pi in is, let's say, C1 or something.
It's problematic because it's near to 0. Near to 0 is problem.
No, near to 0 is good for strong cosmic censorship. Near to 0 is good for strong cosmic censorship.
It's problematic for the stress tensor blows up.
Yeah, the stress tensor blows up. Yeah, but if you want determinism, the stress tensor has to blow up. Well, okay. But as I said in my colloquium on Tuesday, even when the stress tensor blows up and you have a curvature singularity, it's still possible that observers can reach the singularity without being destroyed. And so there's a question of whether we can still make sense of equations of motion for observers even when the curvature blows up. So let me just say a few words about the idea of looking at this using weak solutions. Yeah.
So you this v to the power beta you got because there was an exponential quasi-normal. because there was the quasi-normals decayed exponentially.
Yeah, well, yeah, by definition, they always do. Yeah.
Right. Now, you said that in flat space, that's not the relevant thing
Quasi-normal modes are not the relevant thing in flat
because
space.
the power law dominates.
Yeah.
So that translates into what? In
So
what kind of behavior?
in here, I think, I mean, I haven't thought this through very carefully, but I think what you would see is some different kind of non-analyticity in the mode functions at omega equal to 0. And that's going to basically invalidate all of this.
Right. And would it effectively give you some particular V behavior?
Near the Cauchy horizon. Yes, I think so. If I remember correctly, Chandrasekhar and Hartle discussed this.
So log, is it log V?
It's some, yeah, there's
Because
some,
it's like beta going to 0, roughly.
yeah, there's something involving gamma functions, I think.
Okay.
I can't remember.
In BTC, you will say that there is no difference between superdenims and the extremality line, BTC. So then you will say that you can make beta to be large enough so that staying nice, you can violate this. This was the point.
Well, no, BTC is peculiar, as I'm going to explain probably tomorrow, but it's not for that reason. There's a surprising coincidence that happens for BTC. Yeah. But I'm going to discuss that later. Okay. Okay, let me say a few words about weak solutions, because that was part of the motivation for some of the work on this recently. All right, let's go here. So weak solutions. So the question here is, well, even if the curvature blows up, can we still make sense of the equations of motion? And if we can, then we still have an issue with predictability. So let's look at the Einstein equation with matter. Let's say this matter is our scalar field. So what do we mean by a weak solution of this equation? So we're considering a situation where the metric and the scalar field might be diverging in some way, like we were over here. And we want to ask, can we still make sense of the equations of motion? And the way you do that is you multiply by some compactly supported smooth.
Yeah, I'm still confused about the argument. The strong cosmic censorship says that you will not even find, let's say, C1.
No, so strong cosmic, there are different versions. So strong cosmic censorship comes in different flavors depending on how strong you want the singularity to be at the Cauchy horizon. So strong cosmic censorship says you shouldn't be able to extend beyond the Cauchy horizon as a suitably regular space-time. And then different versions involve saying different things about what you mean by suitably regular. Right. So the physicist version might say you should not be able to extend as a C2 space-time. Okay. So
last time you had stronger conjecture that it will not be even C2. You will not be able to do it as C2 because your stress tensor diverges. But
yeah,
the
exactly.
stronger version of the conjecture said that you will not be able to do it even like C1. Even for C1, you will not be able to.
Well, C1 was talking about the scalar field. So if the scalar field is not C1, then the metric will not be C2 because of the Einstein equation. Okay. Okay, if the stress tensor diverges, then the Ricci tensor will diverge. So the metric then would not be in C2.
And now you're saying even if the scalar field is not C1, it
Yeah.
might actually be okay.
Yeah, exactly. So let me explain briefly how it works. Ultimately, it's not going to be hugely important, but it did motivate some of this work, so I should say something about it. Let's multiply this.
So just one question. In general, aren't we happy with shockwave metrics? Even a metric which has something like a shockwave, which may be continuous but is not even necessarily differentiable at that point.
Shock waves are a little bit special. So I could, let me digress a little bit. So you could ask, what is the minimum regularity you need for the Einstein equation to make sense? And so what is the minimum regularity you need for the initial value problem to be well posed for the Einstein equation? The statement for generic data that's been proved is that the curvature should be square integrable. Okay, so if you start off with initial data, which the curvature could be singular, but as long as it's square integrable, then the Einstein equation is well posed and you can evolve. Shock waves, if you mean like Eichelberg-Sexel delta function type things, actually lie outside that class because they're not a delta function is not square integrable. but nevertheless you can develop a separate theory for interacting shock waves. So this was worked out by Jonathan Luke and Igor Rodniansky a few years ago, and showed that you have well-posedness in that special setting of a few interacting shock waves. Okay, but that's a separate. It doesn't belong to the general well-posedness result that's been established for the Einstein equation. Okay, but so I'm not going to discuss that special case. So let's just ask, in general, what do we mean by a weak solution? So let's take the Einstein equation and multiply by some test function. And basically, the statement is that this should vanish for all test functions. But to make sense of this, we need to do some integrations by parts. So schematically, this is curvature, so that's d gamma plus gamma gamma. Dropping all the constants and indices. Okay, so these are just the Christoffel symbols. So curvature is d gamma plus gamma gamma. I know since we're interested in something that's potentially singular, d gamma is badly behaved, so we integrate by parts to get rid of this derivative. And so we can write this as minus d phi gamma plus phi gamma gamma plus phi t. Okay, and so what we mean by a weak solution is that this expression makes sense and it vanishes for any choice of phi. Okay. So the point was, this expression now doesn't involve derivatives of Christoffel symbols anymore, and so you can still make sense of it even if things are becoming quite singular. Okay, so we have a weak solution if this makes sense. In other words, each term in this equation is finite. And it vanishes for any choice of our test function. And the point is that the terms in this equation can be finite even if something is diverging, as long as that divergence is integrable. Okay? So makes sense here. So gamma has to be square integrable. And t has to be integrable. Okay, so in our case, we can ask, when is the stress tensor coming from our scalar field? When is that integrable at the Cauchy horizon? In other words, so the stress tensor means to calculate the VV component of the stress tensor, I would differentiate this once, square it, and then integrate. And the question is, when is that finite? That's a very simple calculation. And the answer is that beta has to be bigger than a half for it to be finite. Okay. So I should have said, Christodoulou's version of strong cosmic censorship. Generically, we should not have a weak solution.
Beta's bigger than half, roughly because beta is the singularity of a first derivative.
Yeah, I can do
Therefore, it's a singularity of gamma.
I'll do it. It's a trivial calculation.
Yeah.
So in our case, let's look at so TVV, or V minus V minus. That's basically that. And so phi is going like V minus to the beta. Is going like V minus to the beta minus 1. And so if we square that,
That's roughly the same as gamma.
That's 2 beta minus 2. Yeah. And now, well, let me think about that in a minute. Let me just finish this. So now I'm going to integrate this over some region which intersects the Cauchy horizon. So when I integrate with respect to V, I gain a power up here. So we get V minus to the 2 beta minus 1. And so you see that for this to diverge, beta has to be less than a half at V minus equal to 0. Okay.
Right. All first derivatives presumably behave more or less the same way, and therefore gamma also behaves like del V phi. And so gamma is also does the same thing.
Well, you have to be a little bit careful about what we're talking about here. So when you talk about, so what I've been talking about here is the perturbation is the scalar field, and then I back react that. But something else you could talk about is we also allow linearized metric and Maxwell perturbations. And then phi here would essentially behave like the metric perturbation in that linearized setting.
Okay,
Yeah.
but suppose we look at just the back reaction. That would induce a gamma comparable to del V phi.
It would be,
The gamma for that would be comparable to del V phi.
the gamma for this, so well, let's look at it. So the curvature is going like this, so it's going like this. But then we integrate curvature, we get this. So curvature's going like this, so it's doing, beta less than a half causes the gammas to diverge. Good. Okay, so
you probably said this, but
yeah.
Isn't this just a question of how much flux of energy an ingoing observer receives? If that's finite, then you're saying this is smooth.
So I explained this on Tuesday. So it's so the statement is that the Cauchy horizon becomes singular, so tidal forces diverge there. But for the observer, what's relevant is not that divergence, but the cumulative effect of the tidal forces. And so if you calculate the integrated tidal deformation, that turns out to be finite at the Cauchy horizon, at least in the cases people have looked at. So then there's a question of, does it still make sense to continue beyond the Cauchy horizon, even though things are becoming singular there, because it seems that observers are not being destroyed. Okay.
Right, and in this case, this is also the integral of the flux of the energy received by the ingoing observer, whose world line is d by dv. So you just integrate d by du.
Yeah, exactly. Yeah. So good. So that's good. So it's just, it looks like it's the same thing. Yeah. Hydrodynamics. I'm not sure what you mean by that. Oh, you mean you're thinking of some ADS black brain thing? Is that what you mean?
Yeah, that's it. So you can calculate alpha in hydrodynamics, K minus in hydrodynamics. This conjecture gives you an
Okay, but we're not. But we're looking at a spherical black hole here, not a black brain for which we have a hydro description.
I think
Yeah.
saying that for a spherical black hole, if the black hole is big in ADS, they're a very light hydro.
Okay.
They're
But
very light.
okay. We're not in ADS yet, but yeah. Okay.
then this conjecture will give you an upper bound for beta, and that should be checked.
Well, in hydro, you tend to have very slowly decaying things. So my guess is that they're going to give you very small beta, and everything will be fine. Yeah. But in ADS in general, actually, things are much better for strong cosmic censorship, as I'll explain in a bit.
Big black holes will obey stronger.
Yeah. So anyway, so it comes down then to calculating the value of this beta. So if all you care about is whether there's a singularity or not, beta has to be less than 1. Whereas if you're concerned about weak solutions, beta has to be less than a half. Okay.
Right. And just since this came up,
Yeah.
you worked out the scalar case, but nothing would change if this was a metric perturbation.
No, so if you look at Rice-Nordstrom de Sitter, then you can write down decoupled equations for metric and Maxwell perturbations, which are coupled together. So you have two sectors of perturbations, but they each obey a master equation of the form that I've discussed, and so the whole thing goes through there.
Yeah, and once again, it's the quasi-normal mode frequencies that's
exactly the same, yeah. And there's some value of beta, which the value of beta determines how smooth the perturbation is at the Cauchy horizon. Yeah. For long wavelength modes, yeah.
It's set with the size of ADS, right?
Yeah.
It's a massless mode, given mass because there's a size. So it's very light.
Yeah.
Is the rationale for saying the non-linearities will necessarily make this worse?
No. Well, the rationale would be that at least in the asymptotically flat Rice-Nordstrom case, this has been worked out, and the answer is they don't make it worse. Actually, the same has been studied for Rice-Nordstrom de Sitter in spherical symmetry. So, yes, the nonlinear case has been fully understood for spherically symmetric perturbations of Rice-Nordstrom de Sitter. When I say fully understood, I mean taking what mathematicians can do is they can take the decay along the event horizon and translate that into behavior at the Cauchy horizon. And basically it does what you would expect on the basis of a naive extrapolation from this. But doing it without symmetry, of course, is much harder.
No, but solving it in region 1 is not relevant.
Well, so remember, the only reason we're solving in region 1 is to determine this z tilde, and in particular, what we're really determining is the late time behavior along the event horizon. Okay, that's why quasi-normal modes are irrelevant, is they're telling us about that late time behavior.
There is no
Okay.
problem in trusting the mean analysis.
Well, no, there is it is an interesting question. I mean, in principle, you're right. If the linear approximation indicates a divergence, then you shouldn't trust it, and all you can say is that the linear approximation is breaking down, and then you have to go and see what the nonlinearities do. Of course, it would be very surprising if the nonlinearities somehow eliminated the divergence, but they don't. Okay. Yeah. In the cases that have been checked, studied rigorously. I mean, one simple thing you can do is just do a perturbation thing. So you go to second order in perturbation theory and calculate the back reaction perturbatively, and you'll see that there's no funny business.
But even the non-linearities are some local statements. So you're always making some statement about finiteness of some integral. So it's not immediately clear.
Oh, this integral here, you mean? But remember, this thing here is compactly supported. I can take the support of this function to be as small as I like. So it's really a local thing. Yeah, it's what we're trying to understand is local divergences in quantities. It's not some global thing. Yeah, yeah. Good. Okay, so anyway, the question is, what is the value of beta? So back in 1990, Meller and Moss did some calculations, but back then the technology for calculating quasi-normal modes was pretty crude, so it wasn't clear how accurate their results were. But they presented some tentative claim that, in fact, for near extremal Rice-Nordstrom de Sitter, beta is actually bigger than 1. But then subsequently they withdrew that claim for various reasons I don't want to discuss, but we discussed in our paper. So that comes to the recent work. So now people know very well how to calculate quasi-normal modes and have been doing so. So let me tell you the results. So this started with a paper of the end of 2017. So they did Rice and Nordstrom de Sitter with a massless scalar, and they used numerics. And what they found is that beta is over most of the moduli space, black hole moduli space. Okay, so this Christodoulou version is respected over most of the moduli space. But if you look at near extremal black holes, they have beta between 0.5 and 1. No. So they violate this weak solutions form of strong cosmic censorship, but not the strong version, the other version. Let me say that again. So beta less than 1 means that the stress tensor does diverge at the Cauchy horizon. Beta bigger than 0.5 means that divergence is integrable. So you have a divergence, but you can still extend beyond it in the sense of weak solutions. And so that's a violation of the Christodoulou version of strong cosmic censorship. Okay, so the strong version of strong cosmic censorship. So that then inspired us to work on this. Beta bigger than 0.5 is the violation. Beta less than 0.5 would be respecting it. Yeah. So what we did, we looked at gravito electromagnetic perturbations. Again, Rice and Nordstrom de Sitter. Again, calculate the quasi-normal modes numerically. And again, most of the moduli space, you have beta less than a half. But now we found for near extremal black holes. Okay, actually, yeah, I'm now talking about a different type of perturbation, so it's not clear a priori what the critical value of beta is. But let me just tell you what this means is that beta bigger than 2 translates into the metric perturbation being C2 and the Maxwell perturbation being C1 out the Cauchy horizon. Okay, so the curvature is finite at the Cauchy horizon when we perturb. So this is a much worse violation of strong cosmic censorship. It's not just violated Christodoulou's version, but we've actually violated the C2 version. So when we perturb at least a near extremal black hole, and by near extremal I mean a finite neighborhood of extremality, the curvature remains finite at the Cauchy horizon. So we don't form a curvature singularity. And in fact, it gets worse than that. So,
Close to extremality, beta comes to some value.
as you yeah, there is a limiting value at extremality, yeah, and it's always bigger than 2. Yeah, and but related to that, so for any k, we can arrange that beta is bigger than k for a sufficiently large black hole, which is near extremal. So it's not just that the metric is C2 at the horizon. We can actually make it CK for whatever your favorite value of k is by making the black hole near extremal and sufficiently big in units of lambda. So you can make the behavior at the Cauchy horizon as smooth as you like, it seems.
So this computation involves just the computation of the Kocherov movements or even doing the analysis again?
The analysis is all exactly the same as what I've told you. Literally all we have to do is calculate the quasi-normal modes. Well, there's a bit of work because I said you've got these decoupled equations which are written in terms of some master variables and so on, and you have to translate that back into behavior of the actual metric perturbation, and then worry about can you do a gauge transformation to make things smoother than this, blah, 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 blah. But this is the conclusion. Yeah. So generic linear perturbations then can be made arbitrarily smooth at the Cauchy horizon by taking the black hole to be big enough and near extremal. So this is a bad violation of strong cosmic censorship. And so it seems for these black holes you can go through the Cauchy horizon into a region where you cannot predict what will happen. So, Shiraz, you look like you're about to ask a question.
Maybe after.
Okay. Well, by the way, how long should I keep going? Because yesterday I just kept going until you told me to stop. Should I?
I think come to a natural point.
Okay, a natural point would be, okay. Well, when's the cutoff?
1 o'clock.
Okay, all right. There's a natural point fairly soon.
Sorry, maybe since you
Okay.
paused, I can ask.
Yeah.
It's a sort of general question. Let me ask it anyway. You set up the question of cosmic censorship by setting up these sort of finite, well-supported wave packets on these two regions of, two parts of region 1.
Yeah.
But you could have had your wave packet moved to the place which would cause maximal trouble. That is, set up a perturbation that was at very late times along this initial, this black hole, the future black hole event horizon.
You mean I just choose my initial conditions here,
No, I meant down there.
down here?
Yeah, and
Okay.
go all the way in there.
Well, I mean, I can always take my wave packet as long as it's, well, I can do anything I like. I mean, the only assumption is that the wave packet is smooth here, actually.
Right, but I could just send it to very late times. Now, suppose I was outside even region 1, let's say in region 0.
Zero here.
underneath.
Here, 0, okay.
Yes. Is it clear that natural things you do there would not create even worse late time behavior?
No, so let me tell you so Hintz and Vashi, these mathematicians, their analysis was a bit more general. And so what they proved is that if you start from initial data on a surface like this, and the initial data is just smooth on that whole surface, across the horizon, then everything I've said is true. Okay. Yeah. So I think there's a way out, which I will discuss, but it comes back to whether you insist on your initial perturbation being smooth or not.
And what exactly that means?
Yeah.
This is supposed to be true for generic perturbations, right?
Yeah, by generic, though, the question is, what do you mean by generic? So everything I've said so far, by generic, I mean generic smooth initial data. Okay? Yeah.
So you're going to talk about this next
Yeah.
time. But in the case of ADS, if you start perturbing the field theory at late enough times, you will cause trouble, right?
If you allow yourself to throw stuff in from infinity
At late enough times.
with power law decay, for example,
Or just, right.
then that will trigger a problem. Yeah. Yeah.
So just a question about the,
That would say that violation of the
valid-
conjecture, that the conjecture is not valid.
Yeah, but you've done that by hand, by just saying I'm going to throw some stuff in at late time from the boundary.
But it's something you could do.
You could do, yeah, if you want. Yeah, you could do it, but you don't have to do it. And
Pick a surface at finite time, perturbations will be this kind of.
no.
So question about the validity of the linear approximation. If you did what Shiraz was saying and you threw in initial data at late times, then just because there's this exponential blue shift between the early observer and the person who goes in late, you might soon worry about whether the linear approximation is valid, right? Because the relevant energy is really omega times exponential of time. It's like the shockwave analysis people did in ADS.
I think essentially that's all captured in the analysis. I mean, the analysis sees the blue shift. I mean, the blue shift is just a property of the black hole background, and we're studying the wave equation in that background, so it sees that blue shift. And that's why there is a divergence. Right?
No, I understand. But in the situation where you don't have the divergence, I was wondering, I mean, it's like the shockwave analysis where you separate the shockwaves by large enough time, and then you get a huge collision. And in that situation.
This comes back, though, again to the question of, are you allowing yourself to send in things which are not smooth? A shockwave is not smooth. And as I will explain, as soon as you allow things which are not smooth, you can actually rescue the conjecture. But I think most people, I think it depends, do you actually view this shockwave as actually some physical thing, or is it just some approximation to something which is smooth? And if it's an approximation to something that is smooth, then the smooth thing doesn't violate the conjecture. But if you're actually saying fundamentally the perturbation is not smooth, then you can rescue the conjecture.
Okay.
But let me come to that, though. Let me just say a little bit more about what I've said here. So this was all for Rice and Nordstrom de Sitter, but Rice and Nordstrom de Sitter is not very physical because you don't expect charged black holes in nature. So let's look at the much more physical case of Kerr de Sitter, which of course is the real world. So again, this is something we looked at. And the analysis for Kerr de Sitter is essentially the same. Yeah.
Okay. Suppose you set up data at region 0.
Yeah.
There's never a danger of causing trouble at C+.
Well, it depends on what data you're going to set up at region 0. I mean,
Let's do the worst we can.
I mean, if you set up data which is smooth on a surface like that,
Yes.
it's not going to have any problems at C+.
And what's the difference between C+ and the extension of C+ up there?
This,
Yes.
in what way? What do you mean?
I mean, what is the
I mean,
algebraic
the
reason
point is that C+ is in the domain of dependence of this surface. The Cauchy horizon is not in the domain of dependence of anything.
Right. So, but suppose I set up data at your I+, whatever.
Here,
Yeah.
yeah.
Right. Now, once again, C+ is the edge of the domain of dependence.
Well, now you have to be a bit careful because this is at infinity. So, well, also if you just set up data at I+, you only get this region here. So you need more than that.
Okay.
Yeah.
Okay. Yeah.
Yeah. Well, I haven't even told you about ADS yet, but in general in ADS the conjecture isn't violated, so you don't need to do this. But we'll come to that. Yeah. Let me tell you about Kerr de Sitter. Kerr de Sitter. Yes. Kerr de Sitter, the real world. So ADS is not the real world. Rice and Nordstrom is not the real world. But Kerr is the real world and de Sitter is the real world. So this is it, okay? What happens in the real world? Can we jump into a real black hole and enter a region of non-predictability or not? So it turns out, so what we did here is we used geometric optics. So this was an analytic calculation. Calculate quasi-normal frequencies for large angular frequency. So large M quasi-normal. So here I'm assuming a field minus I omega t e to the I m phi. If m is large, you can use WKB or geometric optics to calculate quasi-normal modes. And by doing that, is that beta is less than a half. So, and this is actually saturated at extremity. So any Kerr de Sitter black hole actually respects the strong version of strong cosmic censorship, the Christodoulou version, which says that you can't go beyond the Cauchy horizon in any sense. So that's rather surprising. There's just a difference between Kerr de Sitter and Rice and Nordstrom de Sitter. No, this was for gravitational perturbations as well. Yeah. This is for any Kerr de Sitter. So all.
There is no sense in which this is large black hole. For all
No, any Kerr de Sitter black hole satisfies this. Yeah. So in the real world, strong cosmic censorship seems to be respected. Sorry? Well, if you have a charged black hole, you'd expect it to attract opposite charged stuff and lose its charge. So you could speculate about black holes which are charged with respect to some hidden sector gauge field for which there is no charged matter. And maybe such black holes are pair created in the early universe, but that's a bit crazy, so I'm not going to go there. This is for linearized gravitational perturbations. So Christodoulou, strong cosmic censorship is respected. The conclusion is that, so the statement of strong cosmic censorship is a statement about the theory. Okay, so what we can say is that strong cosmic censorship is badly violated in Einstein-Maxwell theory, but it's respected in pure Einstein gravity. Okay, let me just now say this stuff I was going to say about smoothness or not. So
before you go there,
Yeah.
just one question. Could you please put this in the context of these results by Luke and Dafamos? Weren't they also dealing with this situation? And
put it in the context of what? Sorry, I didn't hear you.
you said strong
Luke and
cosmic
Dafamos.
censorship is respected in the situation of betas for Kerr de Sitter black holes.
Yeah. Oh, so Luke
I
and
was trying to understand the relation of
Okay,
that.
so what they proved, well, first they didn't look at Kerr de Sitter, they looked at just Kerr. But I think what they did could be extended to the de Sitter case. But so far what they've proved is that you can extend the metric across the Cauchy horizon in C0. Okay, so you have a continuous extension. But it's expected that the extension will not be C2 and that it would not satisfy the square integrability condition you need for Christodoulou's version of the conjecture. But so far they haven't written that up. Okay. But
I see, but isn't this in contradiction to what you're saying here?
no, I'm saying that strong cosmic censorship is respected for Kerr de Sitter, and they're saying strong cosmic censorship is respected for Kerr.
But not in the strong form, right? I thought it's only.
No, for Kerr, so for Kerr it hasn't been proved, but it is expected that it will hold. Okay.
I see.
Yeah. So it's only with positive. Charged black hole in flat space, that's now been proved in spherical symmetry. So when you couple to a scalar field. Yeah. Yeah.
Flat space is always better because of the power.
Yeah, exactly. Yeah. Okay. Well, maybe I'll just say the stuff about the smoothness or not. So what you can prove very easily. So this was pointed out by de Fermos and Schlappentock-Rothman. Okay, this is 2 people, not 3 people. So what they said is that if you allow your initial data to be rough, by which they mean not smooth, then the amount of roughness always gets worse at the Cauchy horizon. So maybe I won't go through this. You can see this very easily just by looking at the behavior of mode solutions, actually. Let me just say it. So presumably, well, there is, in fact, so mathematically there will be some minimum degree of regularity that you need for your equations to be well posed, for example. So their statement would be that if you start off with a generic perturbation with that minimum acceptable level of regularity, then the resulting behavior at the Cauchy horizon will not have the same minimum acceptable level of regularity. Okay, that's basically what they proved. So in any, well, so yeah, okay, so there's only one thing there, which is this inequality, which is satisfied by all the black holes I'm going to talk about. Okay, so as long as the surface gravity of the Cauchy horizon is greater than the surface gravity of the event horizon, it's very easy to prove. You can see it. You can just look at mode functions just to see this.
So if the initial data becomes less smooth, then the behavior at the Cauchy horizon will become
even less. Yeah, in fact, why don't I just show you this? I mean, it's quite neat. So the way we understood this, so we discussed this as well in our paper, was if we consider the following perturbation. So we define perturbation to be phi out plus in region 2, 0 in region 1. And we're going to take omega here to be complex. Okay, so it's got a real and imaginary part, which I'll write like this. Okay, so the reason for taking omega to be complex is that I want the field to be continuous, at least, when we move from region 2 to region 1. So what we're constructing is perturbation that looks like this. So here's 1, here's 2. In region 1, the solution is just 0. And in region 2, we've got is propagating outwards. Okay, that's our mode. Okay, so the issue is how smooth is the data here. Okay, so let's call that. So remember our cross-scale coordinates look like this. So this is region 2, this is region 1. So let's work out how smooth this data is as a function of U+. So on this part here, these modes are defined by going. So if we convert that big U to the I omega over kappa plus, and now plugging in omega from up there, this is U plus to the I omega 1, U plus to the gamma. Okay, so you can see, so So the solution goes like u plus to the power gamma for positive u plus, in other words up here, and it's 0 for negative u plus. So how differentiable it is depends on the value of gamma. Okay? And that's the reason we took the frequency to be complex, was to achieve this.
And you think your gamma being positive?
Gamma is positive, yeah, gamma is positive. So the solution is ck at u plus equal to 0 if gamma is bigger than k. Okay, so now we smooth this solution out the Cauchy horizon.
Create perfectly smooth initial data. In that case, the strong cosmic censorship can be violated.
It is violated, yeah. Everything I've said so far.
That will be a fine-tuning problem to create such an initial conditions.
From the rough point of view, it would be fine-tuning. But from the smooth point of view, it's generic. It depends whether you want, whether you're... our title was Taking the Rough with the Smooth, the title of our paper. So if we now look at the behavior of the Cauchy horizon, we've already shown how to decompose the solution into modes at the Cauchy. Scattering coefficients. Okay, so these modes are smooth at the Cauchy horizon, so we need to look at this part. And this part here, they go like e to the minus I omega v, which is minus v minus to the omega I omega on kappa minus. And then so plugging in omega, so v minus, remember, is the coordinate. So we're near the Cauchy horizon, u minus v minus, and we're in region 2 here. So the Cauchy horizon surface v minus equal to 0. So plugging in omega, this is minus v minus to the I omega 1 kappa plus over kappa minus, v minus to the delta. And what is delta? Delta is equal to gamma times kappa plus over kappa minus. And so this inequality that kappa plus is greater than kappa minus...
So we can't hear anything now. We lost the mic.
Okay, okay. So since kappa plus is...
Esther, can you hear us?
Can you... Yes?
Sorry, yes, we can hear you. Can you hear us?
So we can't hear anything from your side. It's totally gone.
Check if the mic is
Can you
on.
hear me now? Can you hear me now?
Can you hear, Habi?
Can you hear now?
Can you hear us?
Shall I
Can you hear me, Suvrat?
They switched off the mic or something. Okay. We can't hear anything. We can see you perfectly clearly, but we can't hear anything. I think the audio went off.
Hello?
Maybe you switched off the mic or something?
No. Two mics are working.
No.
Well, let me write down the final line.
Okay, just think.
The point is that kappa minus is greater than kappa plus, delta is less than gamma. Okay, so the solution is less smooth at the Cauchy horizon than in the initial data.
Phone.
So that's the basic argument. Yeah. You could write your phone number on the board.
I don't know who's got it.
Hi, Subrat. Yeah, hi, Subrat. Can you hear me? In ICTS, you can't hear. Can you hear me?
Yeah, or just say in words, I've just got a few more words about the de Sitter case, and then we can start with anti-de Sitter next time. But have they just lost us completely?
Yeah, I think Subrat's gone out to call us, I think. Since Subrat is one of the most...
Okay. Okay, well, in that case, let's just stop.
Hi, Subrat. Okay, good. I'm keeping the phone on near Harvey. Yeah. Okay, good.
Okay, so I was just explaining why you get this loss of smoothness at the Cauchy horizon. So I'll take the phone to the blackboard. So this is the smoothness at the Cauchy horizon. It's fixed by this power delta. The smoothness of the initial data is fixed by this gamma. And because kappa minus is greater than kappa plus, delta is less than gamma. So the solution is less smooth at the Cauchy horizon than the initial data is. So that was the idea. Okay. So maybe I'll just finish by just commenting on some possible other ways out of the violation of strong cosmic censorship for the Rice-Nordstrom case. So a natural question is, well, when we looked at this, we looked at a scalar field, but it was uncharged. So we're actually looking at Rice-Nordstrom in a model with no charged matter. In other words, it's a model where we can't even form a Rice-Nordstrom black hole. So what happens if we look at the situation where we include charged matter? So we include a charged scalar field. So we looked at that as well, as did some other groups. And our conclusion was that there is still a violation of the Christodoulou version of strong cosmic censorship, but it's much milder. So the value of beta you find is very, 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 very slightly above a half, but it's absolutely tiny.
Does it depend on the charge of the field?
It does, but what you find is there are these, as you approach extremality, there are some oscillations which oscillate above and below a half as you vary the black hole parameters. And this is for essentially any charge of the field. So for physical values of the charge, this is an absolutely tiny neighborhood of extremality where you see a violation. So it makes things better, but it doesn't solve the problem completely. Another natural question is, well, of course, this was entirely classical. What about Hawking radiation? Well, if you include charged matter, then the black hole will radiate it, lose its charge, and move away from extremality.
Sorry, did it depend on the mass of the field as well?
It does, but not in a very interesting way, basically.
So weak gravity.
If you make the mass bigger, it tends to make things smoother at the Cauchy horizon.
Right. So high charge to mass ratios makes things worse?
It's not so much. Yeah, the charge to mass ratio doesn't really play a prominent role in the analysis. So yeah, there's another scale in de Sitter. So it's not like the asymptotically flat case where the charge to mass ratio is important because in order to escape to infinity, you need energy bigger than mass. In the de Sitter case, if you have a charged particle of any mass, then the black hole can radiate it because it can shift it away. Okay, so any charged black hole can decay by emitting charged matter. And so that will push it away from extremality, and then you don't have a problem anymore. About the situation where you just have pure Einstein-Maxwell and no charged matter, what does Hawking radiation do then? Well, then we have to remember that we have two horizons. We have the event horizon and the cosmological horizon, and they both radiate. And so in pure Einstein-Maxwell theory, what happens is that radiation tends to push you to a situation of thermal equilibrium between those two horizons, so they have the same temperature. These are called lukewarm black holes. So they actually have the property that Q is equal to M, it turns out. But these black holes are still sufficiently close to extremality that there's still a violation of strong cosmic censorship. So in that case, Hawking radiation seems not to solve the problem. Okay. So anyway, that's I think, a natural place to stop. I'm going to say much more next time about possible quantum ways of saving strong cosmic censorship in the BTZ case. So, but I think that's all I'm going to say for today. Okay.